Section 15.5, we're continuing on here in Chemistry 3101 with our discussion on chemical shift. And we said how historically the older NMR spectrometers were what were called continuous wave spectrometers, where they simply irradiated the sample with one frequency of wavelength and varied the magnetic field strength. And so that is where the terms downfield and upfield come from. They're historical, but they're still used to this day. They're used in our textbook, and you're going to hear me use them today. So when we're talking about downfield, we're talking about a higher chemical shift. We're talking about de-shielded protons, right, that are going to resonate at a higher energy, because we know that energy is directly proportional to frequency. So if we have higher energy, we could also say these have a higher resonating frequency. And since we divide the frequency of the shift divided by the resonant, or the operating frequency of the spectrometer, again, higher energy or higher frequency, these are going to be de-shielded protons, which show up downfield. And then lower energy protons come upfield, and that is a result of the shielding. Because they are shielded from the externally applied magnetic field, the difference in the energy of their spin states, the alpha and the beta, will be lower. And there you have it. So again, you're going to hear me say higher energy, higher frequency, lower energy, lower frequency, downfield, upfield. They're terms that you're going to hear me say a lot. And when I talk about higher energy or downfield, I'm talking about de-shielded protons. And when I talk about lower energy or lower frequency or upfield, I'm talking about shielded protons. So you need to understand all of these terms and how they all go together. Well, let's talk about how we could de-shield a proton. Right? How could we remove electron density from the environment of a proton? Well, if we just look at a simple alkane, and the simplest possible alkane that we could have is methane, CH4, alkane protons generally resonate or give signals around 1 to 2 parts per million. But if you see what's happening here is we follow these 5 molecules going from methane all the way across from iodo, bromo, chloro to fluoromethane, you see that all 3 of the red protons in each one of these 4 molecules are all chemically equivalent. But what happens to the chemical shift as we go from having methane to having iodomethane to bromomethane to chloromethane to fluoromethane? You see that the chemical shift increases. Why would that be? It increases due to increasing electronegativity of the halogen, right? Fluorine is the most electronegative element in the periodic table. And so it's going to have a really strong dipole going this way. And what does that do? That sucks a lot of electron density away from these 3 protons, which renders them de-shielded and causes them to resonate at a higher frequency, which of course produces a higher chemical shift. And so the stronger the electron withdrawing effect of the halogen, the more pronounced the de-shielding effect is. Similarly, we see that the effect of a halogen is an additive effect, right? If we have only one electronegative element on our methane, so if we have chloromethane, we see that it has a de-shielding effect on the protons. But what if we throw another one in there? Well, we see that the effect is even more pronounced, right? We cause an even greater de-shielding effect. And if we have 3 chlorines, like in chloroform, CHCl3, you can see that the chemical shift of those that one proton, is around 7.3 parts per million. Again, it's just the result of the electron withdrawing effect of the halogen. Something that, if you're very astute, a question that you might ask is, okay, Mr. Dion, well, this makes sense to me, because if you look at any one of these examples that's shown here, right, the electron withdrawing group, the halogens, are always placed on the carbon that has the hydrogens on it anyway. So of course it's going to have some electron withdrawing effect. But what if the protons are farther away? What if the protons are in another part in the molecule? Well, that concept is demonstrated right here in 1-chloropropane. So this is a molecule of 1-chloropropane. You see that the 2 alpha protons are the most de-shielded of all the protons in this molecule, having a chemical shift of 3.3. Well, those are, again, the alpha protons. Once we move it to the beta carbon, you see that the effect is less pronounced. And I'll just tell you, once you get to the gamma carbon, there is no effect. Okay, the chlorine is too far away to have an effect on the gamma carbon. Now you might be wondering, can we quantify? Can you give me some rules, some hard and fast numbers that I could use to quantify the effect on alpha protons to quantify the effect on beta protons? And the answer is yes. But before we do that, we need to look at some baseline values, right? So in order to predict chemical shifts, what we're going to do is we're going to start with the standard chemical shift for the type of proton, a methyl, a methylene, or a methyne. A methyl, if it doesn't have any extra or any external or any extra, I guess is not maybe the best word, but anyhow, if it doesn't have any electron withdrawing groups attached directly to it, it's going to have a baseline of 0.9 parts per million. So 0.9 parts per million. And notice that it's around 0.9 parts per million. It doesn't have to be exactly that. We're just looking at some estimates here. A methylene is going to be a little more deshielded. Those two protons will have a chemical shift of 1.2 parts per million. And when we get to a methyne, we have a chemical shift for this proton that is 1.7 parts per million. And if you're wondering why, if there's no electron withdrawing groups attached here, why would a methyne and a methylene be more deshielded? Well, you remember that carbon is more electronegative than hydrogen. So the more carbons that you place, on the carbon that has, on the alpha carbon, right? The more carbons that we have, the more electron withdrawing groups we have, so to speak. All right, there we go. So those are a baseline. You have to memorize those values because you're going to use them when we apply table 15.1 to adjust the chemical shift depending on the proximity of protons to certain functional groups. If you're wondering, what do you mean by that, Mr. Dion? Well, let me show you right here. Here is table 15.1. This table is actually very, very helpful. And I've split up the table into two slides here. So bear with me. We're going to talk about first about the effect, the electron withdrawing effect or the deshielding effect of an oxygen atom in an alcohol or an ether. So you remember the CH2 group, right? The methylene. Well, we said that the baseline for a methylene was 1.2 parts per million. Well, we know that oxygen is the second most electronegative element in the periodic table. So it's going to have an electron withdrawing effect, won't it? Right? It's definitely going to have that effect. So if you have your methylene, for example, and it's alpha, it's right next door. This is the alpha carbon here. If it's alpha to the hydroxyl of an the oxygen rather, of an alcohol or an ether, this shift is going to increase, or the chemical shift will increase by 2.5 parts per million. So what do? We take 1.2, we add 2.5 to it, and we get an estimate, which is 3.7 parts per million. Now this molecule is ethanol, right? That's the molecule that's used as an example on here. This is just simply ethanol, the same ethanol that's found in alcoholic beverages. Well, you can see that when a scientist runs the NMR spectrum on ethanol, they see that the actual chemical shift of those methylene protons is 3.7 parts per million. Therefore, that tells us that this estimate is pretty darn good. I'd say it's about as accurate as you're going to get for an estimate, isn't it? All right, let's move on from there. And let's talk about the effect of an oxygen of an ester. The effect of the oxygen of an ester is even greater than the oxygen of an alcohol and an ether in that it adds 3 parts per million. 3 parts per million. So let's say we had a methylene group that is alpha to the oxygen of an ester. We add 3 parts per million. So we would take 1.2 and we'd add 3 to it in this case, and we would end up with 4.2 parts per million. This molecule is called ethyl acetate, this ester right here, and I'll talk about that later on in organic chemistry too, even more when we discuss esters. But anyhow, I digress. You see the actual chemical shift is 4.1. So again, the estimate is very, very good. Now you see a little bullet point down here at the bottom. It says, what's the effect on beta protons? Beta protons, okay, will have about 1/5 of the effect of alpha protons. So what's 1/5 of 2.5? Right, for a beta proton, I'll just divide it up here. For a beta proton, you're going to have plus 0.5. What's 1/5 of 3? For a beta proton, you're going to add plus 0.6. And so let's say I wanted to estimate the chemical shift of this methyl group here, the 3 protons in this methyl group here. How would I do it? The baseline for a methyl is 0.9 parts per million, and they are beta to that oxygen, so I'd add 0.5 parts per million. And I would end up with something approximately 1.4 parts per million. Similarly, down here, if I had this methyl group, this CH3 group, again, the baseline for a CH3 is 0.9 parts per million. I'm going to add 1/5 of 3, which is 0.6 parts per million. oops, not ppp, ppm, and I end up with approximately 1.5 parts per million. You will not be given this table on your quizzes or any exams. So it is wise for you to memorize this table. And the more practice that you get, the more confident you're going to become in your memorization of this table. Anyhow, there's one more in table 15.1, and that is the electron withdrawing effect of a carbonyl group from a ketone, an aldehyde, and ester. So if the methylene, if a methylene is alpha to a carbonyl directly, we add 1 part per million. So again, the baseline of a methylene was 1.2. We add 1 to it, and we get 2.2 parts per million. This molecule is called 3-pentanone. If you run the NMR on this in a real NMR spectrometer, not just getting an estimate, you see the actual chemical shift of those protons is 2.4. So again, it's a very good estimate. What about the beta protons? Here we have beta protons here in this methyl group. Yes, I know that this one is equivalent, but I'm just going to use the one on the left-hand side. What's the baseline of a methyl? 0.9 parts per million. And we're going to add 1/5 of 1, which is 0.2 parts per million, right? So we add 0.2 parts per million, and we end up with approximately 1.1 parts per million. You'd be shocked how often you can use the table 15.1 when you're doing practice problems in our book. All right, so table 15.1, again, I won't provide you with that table. However, it is wise for you to memorize the effect of a carbonyl group, the oxygen of an ester, and the oxygen of an alcohol or an ether, because those functional groups come up all the time in organic chemistry. Let's move on from there, still in the vein of chemical shift. We're still in the same section, and talk about what's called anisotropic effects. We look at a lot of aromatic compounds in Organic Chemistry 1 and Organic Chemistry 2, right? Everybody here is familiar, hopefully, by now with an aromatic ring. Okay, this is an aromatic ring. This is actually just benzene. And you see that all 6 of the protons on benzene are chemically equivalent. And so, yeah, all chemically equivalent. But what happens is, when we subject benzene to an external magnetic field, the pi electrons start to circulate and they produce a magnetic field which causes diamagnetic anisotropy. And I'm going to discuss that in a second. But that's why when we draw aromatic rings, sometimes it's helpful just to draw a circle like this that represents the fact that the double bonds are actually in resonance. So diamagnetic anisotropy is simply nothing more than this, that different regions of space in our molecule, our benzene molecule, are going to be characterized by different magnetic field strengths, right? You're subjecting this benzene molecule to the externally applied magnetic field, but what the point of diamagnetic anisotropy is this, is that different regions of the molecule are going to have a different effect or a different net applied magnetic field because of the induced magnetic field caused by the circulating electrons. And we have the pattern of the flow of the magnetic field that's produced shown here. So you can see that inside the ring, right, inside the ring like this, we have a magnetic field that opposes the applied magnetic field, right? That means that this section is going to be shielded, right? The inside of the ring is going to be shielded. However, look at the outside of the ring where the protons actually are. We see that there's a magnetic field there that actually aligns with the applied magnetic field. And so these protons are going to be de-shielded by this induced magnetic field. What does that mean if they're de-shielded? I'll go over it again. If they're de-shielded, that means that they feel even more of the applied magnetic field. Therefore, the difference in energy between the alpha and the beta spin states is going to be greater. That means it's going to take more energy or a higher frequency to cause them to come into resonance, which in turn means that the protons on an aromatic ring are going to have a higher chemical shift. They have a high chemical shift. All right. Anyhow, this is just rehashing what I said already. But again, the protons outside of the ring, which are the only protons we have in benzene, the 6 protons are all on the outside of the ring, they have an increased magnetic field, and therefore they are de-shielded. And so aromatic protons, generally speaking, come out in the range of around 7 parts per million. It can be a little more, it can be a little less, depending on the molecule or the substitution on the aromatic ring, but they come out with a high chemical shift. If you take a look at this molecule here, this is called ethyl benzene. Okay, so we take a benzene molecule and you put an ethyl group on it. Check it out. You see that there's 3 types of unique protons on the aromatic ring. Okay, again, by symmetry, you see that these 2 protons are identical, right? These 2 protons are identical or chemically equivalent, right? And this proton is unique. So we have 3 types of aromatic protons, and I told you that they are going to have, or going to require, excuse me, more energy to spin flip. And so the aromatic protons, I said, come out around 7 parts per million. Now, we get some complex splitting here. We can't really say that that's a doublet or a quartet, and I'll get into that more later on. But the idea is that because of diamagnetic anisotropy, these protons resonate at a high frequency and come out at a high chemical shift, around 7 parts per million. Something else that I want to point out to you is this. You remember 5 minutes ago, I told you that the baseline for a methylene, right? This is a CH2 and this is a CH3. I told you that the baseline for a CH2 was 1.2 parts per million, didn't I? Well, if you look at these 2 signals down here that are upfield, I'll just tell you, and we'll get into this more later on, but this one here comes from the CH2, okay? And you see that it's definitely greater than 1.2 parts per million, right? 1.2 is down here. It's at what, 2.56, something like that, 2.6 parts per million. The reason why is probably exactly what you're thinking, that the effect of diamagnetic anisotropy is also going to affect protons that are close to the aromatic ring, right? Since these 2 protons are close to the aromatic ring, they also experience a little bit of that de-shielding effect. Anyhow, if you open up any organic chemistry textbook in the world, if you open up your lab manual or any organic chemistry lab manual, if you go on the internet and look up NMR, if you were to Google NMR chemical shifts, you're going to find literally Avogadro's number of, tables that show chemical shifts for different protons. I will provide you with a table similar to this one for your quiz. However, it would be wise for you to familiarize yourself with the chemical shifts of common types of protons. Why? Because they're common. They show up so much, it gets kind of annoying to have to refer back to a table every time for every single proton under the sun. That would be really an annoyance. And so we already looked at the first 3 here, the methyl, the methylene, and the methyne, and we said what their chemical shifts are. We said that an aromatic proton is in the neighborhood of 7. Here they've expanded it to 6.5 to 8 parts per million. Well, let's take a look at the other ones. If we look at an allylic proton, right, you need to know the difference between allylic and vinylic. An allylic proton has a chemical shift of around 2, whereas a vinylic proton is significantly more de-shielded, and that is also a result of diamagnetic anisotropy. How it affects, or how the electrons circulate in the pi bond of a vinyl group or an allyl group or an alkynyl or whatever, it's not covered in our textbook, so I'm not going to go over it, but I'll just kind of mention it. Again, so you have to be familiar with those values. And alcohol has a really broad range of chemical shifts, the alcohol proton. It can range anywhere from 2 to 5 parts per million. The same thing with an alkyl halide, and that's kind of where we started this morning, right? We were looking at different alkyl halides, and you saw that they had a wide range of chemical shifts between 2 and 4 parts per million. When you have a terminal alkyne, and all a terminal alkyne means is that you have a hydrogen attached to an sp hybridized carbon, we have a chemical shift of around 2.5 parts per million. We saw on the previous slide that the effect of diamagnetic anisotropy causes de-shielding of groups that are attached directly to an aromatic ring. So instead of a methyl, which has a baseline of 0.9, an aromatic methyl has a higher chemical shift, around 2.5. We saw that again on the previous slide. What am I missing here? I think the only ones I left out are the aldehyde and the carboxylic acid. These are the kings of the castle, right? They have the highest chemical shift, so usually they're the easiest ones, or I would say easier for students to remember. An aldehyde proton, whenever you have a chemical shift of around 10 parts per million in Organic Chemistry 1, it's pretty much a dead giveaway that you've got an aldehyde. And whenever you have a chemical shift around 12 parts per million, again, I would say that's kind of a dead giveaway that you've got a carboxylic acid. If you're thinking about all the forms of spectroscopy that you've learned, IR and NMR, you're probably thinking, man, if I ever see an IR and an NMR for a carboxylic acid, I would never get that wrong under any circumstances, right? Because you know that the absorbance of the hydroxyl of a carboxylic acid in the infrared spectrum is very broad. And if you see a chemical shift at 12 parts per million, you're going to say, well, hey, I've got a carboxylic acid. And you would be absolutely correct in making that assumption. Okay, there we go. So chemical shifts. With that in mind, let's take a look at a practice problem. This is problem 15.10. I just selected a couple of them here. And it says, for each of the following compounds, draw the expected, identify the expected chemical shift for each type of proton. So I'm going to walk through this with you kind of slowly. We'll start with this first compound. You see we got some cool functional groups in here. We got an aldehyde, we got an alkene, and we have an alkyne. Well, if we start with the aldehydic proton, according to the table that we looked at on the last slide, and I'm not going to do this for every one, this should have a chemical shift of around 10 parts per million. And so we'll write here that this proton should have a chemical shift of around 10 parts per million. Here we have a methylene, right? A CH2. Well, I'm going to circle both of these protons because they're both chemically equivalent. If you notice, here we have a vinylic carbon, which renders this an allylic carbon. So these are allylic, and allylic protons have a chemical shift of around 2 parts per million. But you also notice that it's alpha to the carbonyl, right? It's alpha to this carbonyl here. And we said that the electron withdrawing effect of the carbonyl causes an increase in chemical shift of 1 part per million. So we have alpha carbonyl, I'll just write it like that. So we have 2 plus 1, which is going to give us around 3 parts per million. If we look at this proton here, this is a vinylic proton, So vinylic protons come out around 4.5 to 6.5 parts per million. Now, if you're very astute, you might be saying, well, Mr. Dion, this carbon is beta to the carbonyl, so you should add 0.2, so it should be 4.7 to 6.7. Well, our book didn't do that in the solutions manual, and I want to be consistent with the solutions manual. Why didn't he include that? My guess is that since it's only 0.2 and there's such a wide range for the vinylic protons, that 4.5 to 6.5 would be acceptable. Similarly, here, oops, I'll keep using my red pen. We have another vinylic proton. So this one is also vinylic, has a chemical shift of 4.5 to 6.5 parts per million. Here we have another methylene. These two protons are also allylic. Remember, we have the double bond here. This is the vinylic carbon. This is the allylic carbon. So these ones are allylic. So they're going to have a chemical shift of around 2 parts per million. What else? We have a methylene here, a CH2 here. These two protons are chemically equivalent. There's nothing that's going to cause any great deshielding effect here. And so we'll give these a baseline of 1.2 parts per million. And then we said if we have a terminal alkyne, that the chemical shift of the proton of a terminal alkyne is around 2.5 parts per million. Now that might seem a little daunting that I went over those pretty quickly. Okay, but I've taught the class long enough to know that it's going to take some time for you to sit down and look at these before they start to really crystallize in your mind. Anyhow, let's take a look at the next one. I'm going to draw in the protons here, these two protons. Here we have a methyl group, CH3. Here we have a methylene. And here we have another methylene. Let's start on the right-hand side this time, just for fun. We know that the proton in a hydroxyl, again, an alcohol, is going to resonate at a frequency that's going to produce a chemical shift between 2 and 5 parts per million. If you're wondering, where are you getting that information? Look, I'm just looking here. An alcohol is going to resonate between 2 and 5 parts per million. Okay, there we go. Next, we have a methylene. We said that the baseline of a methylene was 1.2 parts per million. However, this methylene is alpha to an oxygen. And remember that an oxygen of an alcohol or an ether is going to increase the chemical shift by what? 2.5 parts per million. So we take 1.2 and we add 2.5 parts per million, and we end up with around 2.7 parts per million. The next methylene is beta to the oxygen, but it's also allylic. So it's a double whammy. Here we've got allylic protons. So these are allylic, which have a chemical shift of around 2, but it's also beta to the oxygen. Okay, so we're going to add 1/5 of 2.5. So we take 2 plus 0.5, and we end up with around 2.5 parts per million. What's next? We have this methyl group. All 3 protons are always equivalent in a methyl group. They are all allylic. So allylic, that means they're going to have a chemical shift of around 2 parts per million. Again, if you're wondering where do you get that, right here, allylic protons have a chemical shift of around 2. And the last ones are vinylic. Okay, the last 2 are vinylic protons. And so we'll circle these ones and we'll say vinylic. And they're going to have a chemical shift between 4.5 to 6.5 parts per million, like that. And so that is how we analyze the different types of protons in an organic molecule, and we estimate their chemical shifts. So that covers the whole section on chemical shifts. Of course, chemical shift is going to come up over and over and over. It's because I didn't add them correctly. So there you go. This should be 3.7, shouldn't it? There we go. All right. 1.2 plus 2.5 is 3.7. There we go. All right. So let's move on from there, and let's move off of chemical shift, and let's move on to the subject of integration. So remember the first NMR spectrum I showed you? We said, well, we have chemical shift. So that is the number of unique types of protons. And then we have integration, and then we also have multiplicity. Well, now we're on to integration. If you look at an NMR spectrum, just like this one here, the actual area under the peaks or the signals quantify the relative number of protons. Notice that it says the relative number of protons. It doesn't tell us the exact number of protons, but it tells us the relative number. So what I'm saying is this: if you could actually, trace out all the area, well, that doesn't work very well, does it? If you could, shade in all the area under here, and then you were to measure the area under here, and then you were to compare it to the area under this one here, like this, okay, and you were to compare the areas of all 4 of these signals. I'm not going to do it for all of them. You see that their relative areas are 27 to 40.2 to 28.4 to 42.2. Again, these are relative areas. We're not going to have 40.2 protons in a molecule, right? But again, what they give you is the relative number of protons. Now, what does a spectrometer do? Sometimes you can set up your spectrometer such that it will literally just spit out the integration values to you in numerical form like this. Other times we get what are called step curves. This thing here, this is called a step curve. This is a step curve. The way that you interpret a step curve is old-fashioned. You go to your desk, you grab something, it's called a ruler, okay? And you literally put the ruler on the piece of paper, right? And you measure, okay? So that's a pretty crummy looking ruler. But hopefully you get the idea that you measure the height of this curve from this horizontal line to this one, from this one to this one, right? So you go from the top horizontal part to the bottom, and you measure the heights of all of these step curves in millimeters, and you literally compare the heights, and that will give you the relative numbers of protons represented by each one of the signals. So how do we figure out exactly how many protons are represented by each one of these signals? Well, what we would do is we would divide each one of these integration values by the lowest value. So if we divide all of them by 27, right? If you divide 27 by 27, what do you get? 1. If you divide 40.2 by 27, you get 1.48. Then we get 1.05 and 1.56. Again, these are relative numbers of protons. You're like, Mr. Dion, there's no such thing as 1.05 protons. I agree, my friend. I agree. However, these numbers are usually not going to be exact. Okay, they're going to give you a very, very good estimate of what they actually are. Now, again, there's no such thing as 1.5 protons, and you see here I have 1.5 and 1.5 approximately. what if I take this entire thing, all of these integration values, and I multiply them by 2? Then I'm going to end up with just whole numbers. Okay. Now, I know that 2.96 and 0.10 and 0.12, I know those aren't whole numbers, but they're close enough to say that, you know, this kind of looks like a 2, a 3, a 2, and a 3. So that is what we do with our integration. So what we say is that the relative number of protons represented by this signal would be 2 to 3 to 2 for this one to 3. Now, if you add up 2 plus 3 plus 2 plus 3, you get 10. You're like, Mr. Dion, there's 10 protons in this organic molecule. I would say maybe yeah, maybe no. It depends. You might be wondering, what do you mean by that? Well, I'll give you some examples in a second. But before we do that, I just want to mention one more historical point here about integration, is that besides using step curve and integration values, there's one other way that I know of to calculate integration values. You want to hear it? It's kind of funny. Back in the olden days, they used to print out NMR spectra on really heavy stock paper, and they would literally take, and Mr. Dion wouldn't do this because I'm not good at cutting, but they would literally take a pair of scissors and they would cut out all the signals like this, okay? Then they'd cut out this one, okay? And since it was on a heavy stock paper, they would literally cut them out and weigh them on a balance. And they would compare them by mass, the mass of the paper on the balance, okay? Might sound kind of low tech, but it worked, all right? Anyhow, there you go. So integration. Well, what if we had this molecule right here? This is called 3-pentanone. We actually saw it earlier today, 3-pentanone. And if you want to Google the NMR spectrum of 3-pentanone, you could, but it's on the next slide. So how many unique types of protons are there in 3-pentanone? Well, I have a methylene here, which is chemically equivalent to this methylene here, right? Because of symmetry, rotational symmetry in the molecule. I also have a methyl group here, and I have a methyl group here, and those are also chemically equivalent based on the rotational symmetry. But what's interesting is that when you run the NMR spectrum of this compound, you should get 2 signals, right? We've got 2 unique types of protons, so you get 1, 2 total signals. If we look at the integration values, though, we see that if we take 32.5 and we divide it by 32.5, you get 1. And if you do the same thing here, 32.5, you end up with 1.48, which is close enough to 1.5. If I was to multiply 1 and 1.5 by 2, I would get 2 to 3. And you think, okay, well, 2 plus 3. If I didn't know the structure of this compound, you might say, well, hey, there's going to be 5 protons. That's it, cut and dried. Not necessarily, because the absolute ratio here is actually 4 to 6. And so in order for us to be able to determine the exact or the absolute ratio of the protons, we'd have to know the molecular formula, right? But you can see how you could connect the dots very easily. If you knew that the relative ratio of protons is 2 to 3, and you knew that there's 10 protons in the compound, right? Then you know the actual ratio must be 4 to 6, right? You've got 4 protons represented by this signal, and you've got 6 protons represented by this signal. Give me a thumbs up if that makes some sense to you. Just multiplying numbers in our head, really, and doing a little bit of division. Okay, cool, great, yeah. Well, with all that in mind, let's take a look at some examples. And these examples come, again, directly from your textbook. So this is question 15.11. It says a compound with this molecular formula, C5H10O2, has the following NMR spectrum. How many protons are giving rise to each signal? So again, we've got 10 protons, right? We got 10 H's in this molecule. Here are the relative integration values shown down here at the bottom. If we divide each one of these by 33.2, right? 33.2 is the smallest number here. And I'm not going to write it out for all of them because I know you know how to do simple math, but 33.2, you end up with 1. You do the same thing here. You end up with approximately 1.5. Here you end up with 1, and here you end up with approximately 1.5. Well, if I tally up 1 plus 1.5, that gives me 2.5, and then the total would be 5. There aren't 5 protons in the molecule, are there? Right? If I was to, again, I'm just adding up all these numbers in blue. 1 plus 1.5 plus 1 plus 1.5 gives you 5. 10 is the double of 5. So if I take all of these and I multiply them by 2, Then I see that this signal represents 2 protons. This signal represents 3 protons. This signal represents 2 protons, and this signal also represents 3 protons, right? Again, you can see the correlation, right? 2 compared to 33.2, 3 to 48.4, and then 2 compared to 33 again, and 3 compared to 48 again. So we can draw a conclusion very quickly as to the number of protons that are represented by each signal. Give me a thumbs up if that makes sense to you. And then we'll take a look at the next example. Integration. Okay, good. All right, well, let's move on from there. Let's try one more. And I'm going to get you guys to try and solve this one for me. Here we have another compound that's got 10 protons in it. So again, we've got 10 protons in the entire molecule. And now we have all of our integration values down here at the bottom. We have 17.1, 87.1, 18.7, and 51.1. What we're going to do is you're going to divide each one of these by 17.1, divide by 17.1, divide by 17.1, divide by 17.1. When you do that, you end up with some numbers. You end up with 1. You end up with approximately 5. Here you end up with approximately 1. I know it's a little greater than 1, but it's close enough for jazz. And then here we end up with approximately 3. What number do you get when you add up 1 plus 5 plus 1 plus 3? You end up with 10. And so I said I was going to ask you a question, but I guess I'm not going to. So that means this singlet out here, what I mean by singlet is that it's one single peak, represents 1 proton. All of this here represents 5 protons. This little guy right here, you can zoom in on it. This one here represents 1 proton. And lastly, this guy down here, this signal, represents 3 protons. Okay, and that is, again, how we use integration. Again, I could give you a step curve, and you'd have to bust out a ruler. But seeing as you're going to write your quiz on a computer, I'm probably not going to get you to hold a ruler up to the screen. But, you know, next semester, if you're taking organic chemistry with me, I might give you one where you have to use a ruler to measure the step curves. Okay, that brings us to what I think is probably the most important part of the information that we can get from, or one of the more important parts of the information that we can get from the NMR spectrum, that is the multiplicity. You've heard some of these words slip out of my mouth throughout this lecture: singlet, doublet. You probably haven't heard me say triplet, quartet, and the rest. But a singlet simply means we have 1 peak in a signal. A doublet means we have 2 peaks in a signal. A triplet, which has this nice symmetrical shape to it like that, that means we've got 3 peaks in a signal. A quartet is also symmetrical. You see that all the rest of them are, right? A quartet has 4 peaks. A quintet has 5 peaks. A sextet has 6 peaks. And a septet has 7 peaks in a signal. Don't believe me? You can count them. Right? We have 1, 2, 3, 4, 5, 6, 7. Right? If you go over to the sextet, it's pretty obvious, I think, that you get 6 peaks there. Anyhow, so that's what a singlet, a doublet, a triplet, a quartet, quintet, sextet, and septet are. And what's so great about these? You might be wondering, okay, well, where's this going to take us? Remember, I promised you way back at the beginning when we first started talking about NMR spectroscopy, I said it gives you information about the connectivity, right? Chemical shift didn't tell us anything about connectivity, did it? All it told us about was the electronic environment in which the proton is existing. Next, we looked at integration. All that tells us about is the number of protons that are represented by each signal. But now multiplicity, haha, this is where it gets really interesting, because now we're going to get information about the way the molecule is connected together. It's not going to just spit it out for us like, here's the answer or anything like that. It's going to give us clues as to how the molecule is connected together. And then we're going to have to put them all together. Okay, we're going to have to put them all together. All right. The quintet is symmetrical enough to me, Jonathan. It looks symmetrical enough to me. It's not perfect, but it's, you know, looks pretty good. They're all, you know, getting bigger as you go towards the center. So that's symmetrical enough. All right, there we go. So What does multiplicity tell us? Let's say you're a proton, or let's say we're dealing with a proton, HA. What kind of environment is HA in, right? How many peaks are going to be in the signal of HA? Well, let's imagine that HA and HB are not chemically equivalent. Okay, that's why we're using two different colors, the red proton and the blue proton. They are in different environments. Well, remember that HB, okay, it's got spin, doesn't it? It has nuclear spin. Therefore, it's going to have an alpha spin state and a beta spin state. Therefore, it's going to have a magnetic moment. If it's got a magnetic moment, that means it's got a magnetic field. If it's got a magnetic field, that means that the magnetic field of the HB proton is going to have an effect on HA, isn't it? Well, what about the magnetic field of HB? Well, HB can be in an alpha spin state. It can be aligned with the applied magnetic field, okay? And it can also be aligned in a beta spin state or against the magnetic field, which is shown here, okay? So HB can either spin with the magnetic field or it can spin in a direction that is against the applied magnetic field. What does that mean? Okay, that means that HA is going to exist in an environment where sometimes it has the effect of HB going with the magnetic field, which is going to cause a de-shielding effect. And then sometimes HB is going to be going against the magnetic field, which is going to cause a de-shielding, a shielding effect, sorry. And so we end up with two different environments, and thus we end up with two different signals. Give me a thumbs up if that makes some sense to you. Now, that was my full-on treatment of the concept. I can, make it even a little simpler, but to give me a thumbs up if that makes some sense to you. Okay. Again, if you want me to make it simpler, here you go. We have two protons. They are not chemically equivalent. HA is going to be affected by the magnetic field of HB. And since HB has two possible spin states, alpha and beta, that means that it can either have a shielding effect or a de-shielding effect on HA. Okay? If HA is de-shielded, it's going to give you a signal that's going to be a little further downfield, right? This is the result of the de-shielding effect, de-shielded, so to speak. I can spell, okay? And then this one is going to be a little bit shielded. Okay, so we end up with two different peaks in the signal. So we end up with a doublet. Now give me a thumbs up if it makes sense. That's my second explanation. Two spin states for HB, and therefore it's kind of like two little micro environments for HA to exist in, and they're different. One's going to produce a shielding effect. The other one produces a de-shielding effect. All right. Okay, good. If you've gone ahead and read the book, which I hope you all did, we're going to get into this in a little bit, but this is called the N+1 rule, okay? The number of peaks in a signal is going to be related to the number of neighboring protons that are chemically equivalent plus 1. So since we have one proton next door to HA, you take 1 plus 1 and you get 2, and you end up with a doublet. Don't believe me? Take a look at this HA. This HA has two neighbors, right? It's got two HBs. If we use the N+1 rule, neighbor plus 1, well, we got two neighbors. 2 plus 1 equals 3, and therefore we end up with a triplet, which is great. And the N+1 rule will be applied a lot of the time by you. But what I want you to understand is that how HB, the two of them, affects the frequency of the resonance of HA. Okay, both HBs can be spinning in the same direction as the applied magnetic field, which is going to cause de-shielding. Right? It's going to have a greater magnetic field, and therefore it's going to take more energy to flip or to resonate between the alpha and beta spin state, and therefore it's going to absorb a higher frequency of electromagnetic radiation, and therefore it's going to be a little bit deshielded. And that's why we end up with one that's a little bit deshielded. Then we can also have a scenario where each proton is aligned with and against the magnetic field. And since there's two protons, there's two scenarios. Okay, that's going to be the one in the middle. And then I have a scenario where both protons are shielding HA from the magnetic field, and therefore that's going to produce this signal here. And statistically, we have a 1 to 2 to 1 possibility for these different electronic environments. And you see that the ratio of the heights of the peaks in the signal is pretty much 1 to 2 to 1. It's pretty close to that. Okay, so we end up with a triplet. Same thing would happen if we had a methyl group neighboring. Okay, same thing again. Look, we've got 1, 2, 3 protons. You can have 4 different situations. You can have all of them aligned with the magnetic field, which is going to cause deshielding. You can have all of them aligned against the magnetic field. You can have 2 against and 1 with, or you can have 2 with and 1 against. And you can see that the ratio of these possible scenarios is 1 to 3 to 3 to 1. Well, if you look at the quartet that's produced, you see the ratio of the peaks in the signal is 1 to 3 to 3 to 1, approximately. Okay, it's close enough. All right. So again, applying the n+1 rule, neighbors, there are 4 of them, 4 plus 1, excuse me, there are 3 of them, 3 neighbors in a methyl group. 3 plus 1 gives you 4, and that is why we get a quartet. So that explains multiplicity. That's my best explanation I can give you for multiplicity. This table shows how the trend continues as we go to a quartet, quintet, sextet, septet, which follows Pascal's triangle, which I'm not going to get into in a lot of detail. But just by analyzing the splitting pattern of a proton NMR, you can determine how many equivalent protons you have on the carbons next door or adjacent carbons. So we have n number of neighboring protons that are chemically equivalent. Then we're going to have n+1 peaks in the signal, and we call that the n+1 rule. I know enough to know that my students are going to apply this over and over and over because it's a, again, you hear me say this all the time. I don't like to use the word simple in organic chemistry, but most students are pretty good at adding 1 to something, okay? If I give you a number and I say add 1 to it, students are usually pretty rock solid on that. Well, 3 key rules to remember for splitting. Equivalent protons are not going to split each other because they resonate together. The example that's given in the book for this, I think, is something like 1,2-dichloroethane. So if you draw this molecule, you have a methylene here, and you have a methylene here. These 2 protons are chemically equivalent. They have 2 next door neighbors. It might be a knee-jerk to say that for this, I'd get a triplet, okay? But you won't get n+1. You won't be able to apply that rule because both of these protons are equivalent. You know what I mean? Okay, right? These 2 protons and these 2 protons are chemically equivalent based off of rotation. Anyhow, another rule is that in order for protons to split each other, in order to have spin-spin splitting, the protons have to be within 2 or 3 bonds from one another. If you have protons that are on the same carbon, we call those geminal protons, right? Gemini, they're twins, they're on the same carbon. If they are non-equivalent, meaning that they are diastereotopic, then we can observe splitting. Most of the splitting that we're going to look at in this class, however, will be vicinal splitting. Okay, I think we're going to look at vicinal splitting probably 99% of the time. So you go to the next door neighbor, right? And you look at the protons on the next door neighbor, right? This is a carbon, this is its next door neighbor. You can have spin-spin splitting that comes from carbons that are further apart, like this one here. We would call that a long-range coupling. It is not covered in our textbook. If you want to know more about it, you could go ahead and look it up. Long-range coupling is usually only observed in molecules that are more rigid, like maybe a bicyclic molecule. Anyhow, you can imagine that NMR is a very deep topic, and we're only really scratching the surface of the subject in Organic Chemistry 1. Another rule is that the n+1 rule only applies to protons that are all equivalent. So, for example, if you wanted to figure out what the splitting pattern is for the proton that's highlighted in red here, you might think, based off of what I told you, that it would be a triplet. If you're like, I'm not sure what it would be, Mr. Dion, let me show you why you might think it's a triplet. Because here's a carbon, here's its next door neighbor, here's the other next door neighbor. On this carbon, I have a hydrogen, and on this carbon, I have a hydrogen here. Okay, we'll call this, HA, we'll call this HB and HC. Okay, well, HB and HC are not chemically equivalent, right? HB is not, HB, let me write it like this, is not the same thing as HC. You can clearly see that they are very different protons. So if you didn't understand that, it might be a knee-jerk reaction to say, well, I've got two neighbors, 2 + 1 is 3, therefore I'm going to get a simple triplet. But in fact, you wouldn't get that. You'd get complex splitting. I'm going to tell, and if you're like, what would you actually get? Well, I'll tell you. Let me back up here. Let me erase some of this spinach to show you. Here's the answer, is that HA would be split by HC, right? 1 + 1 gives you 2, so it would give you a doublet. And HA would also be split by HB, which would also give you a doublet, right? 1 + 1. So you actually end up with what's called a doublet of doublets. And you're like, that wasn't on the first slide of multiplicity. No, it wasn't. A doublet of doublets would look something like this, where you'd have, two that are the same height, and then you'd have two more that are the same height right here. So this would be a doublet of doublets. Anyhow, again, we're not really going to talk about complex splitting because it's not covered in the ACS. It is covered in our textbook, and if you want to read it, of course, take the time to do that. What else? What else can we say about splitting? Well, let's say we had a molecule like this one here. We have HA, both of them are chemically equivalent. We have HBs, all three of those are chemically equivalent. How many, or what kind of signal are we going to see for the HAs? What kind of signal will we see? Well, for the two HAs, we have N + 1. How many next door neighbors are there? There are three HBs. So we have 3 + 1, which gives us 4. So HA is going to produce a quartet. We do the same treatment for the HBs. We have N + 1. How many next door neighbors are there? There are 2. So we have 2 + 1, and that gives us 3. And so for HB, we get a triplet. Now, how would we know, just by looking at an NMR spectrum, that these two signals are actually splitting each other? How do we know that they're actually causing the splitting of one another? The answer is, we know that they are splitting each other by looking at the difference, or the distance, between the peaks. Okay, you measure the distance here. It's measured in hertz. You measure the distance here in hertz, and then you do the same thing over here. If the distances are all the same, then they're splitting each other. The distance between the peaks in a splitting pattern, we call that a J value. I won't use that a whole lot. Instead of J value, I will usually tell you what it's called a coupling constant. So protons that split each other have the same coupling constant. This is a very important point, that protons that are going to split one another, okay, that you can apply the N + 1 rule, are going to have the same coupling constant. All you really need to know is that they're going to have the same distance between their peaks. Well, what's the significance, or there is more significance, I should say, to the coupling constant. And way back in last lecture, I told you that the higher the operating frequency of your instrument, the more expensive it is, right? They cost more money. Well, just like a high definition TV, Mr. Dion is kind of out of the loop with respect to what kind of TVs you can buy at Costco or Best Buy or from Jeff Bezos or whatever nowadays. But the idea is this: if I was to go to a pawn shop and, let's say, buy a TV that I have to plug in an antenna to, the TV was, built in 1990, it's a tube TV. Can I, hook up a VCR and watch a movie on it? Sure, absolutely I can. And I can get the whole story from it. But the resolution, or the picture, is not going to be as good as if I go to Costco right now and I buy the highest definition TV that they have, and I put in a Blu-ray DVD or whatever, and I watch the movie in high def, right? I'm going to get the same story, but the picture is going to be much clearer, isn't it? And that is the difference between, say, a 300 megahertz spectrometer and a 60 megahertz spectrometer. If you were to run the NMR on this ester here on a 60 megahertz spectrometer, well, this methylene should be a quartet, shouldn't it? Because it has N+1 and it's got 3 neighbors, so 3 plus 1 is 4. But you see that the quartet is supposed to be the ratio of 1 to 3 to 3 to 1. Well, where's the other part of that quartet? It's actually buried under these 2 protons right here. So when I buy a more expensive spectrometer, this is a 300 megahertz here. Look what happens now. I get the same story. I get that quartet and that singlet, but now I can see all of my beautiful quartet like that. So we get better resolution when we have a higher field spectrometer and we have less overlapping. Now, the book goes into more detail about that, and I could go into that right now, but I know that I'm talking a lot. This lecture just requires a lot of background, and so I'm not going to go into it in more detail, but you can take a look at how each part per million, how many hertz it represents depending on the type of spectrometer or the field strength of the spectrometer or the operating frequency of the spectrometer, which are all related. Anyhow, here we go. Here's that coupling constant thing again. Remember the coupling constant I said if these sets of protons are splitting one another, that JAB is going to be equal to JBA, like this. And that's just a sassy way of saying that these 2 protons produce a quartet because they're split by these protons. And these 3 protons are going to produce a triplet because they're split by these 2 protons. Well, you can see that the relative distances between the peaks, just by using your eyeball, they look pretty similar to me, okay? They look very close. But if you had a triplet in a quartet like this, it might be a knee-jerk reaction to say that this is an ethyl group, just like the one up here. But it's probably not, because you can see that the distance between the peaks here is much larger than here, than in this one. And so these, I mean, is this a quartet? Yes. Is this a triplet? Also, yes. Are they splitting each other? No, because their coupling constant is not the same. All right. So based off of the N+1 rule, what are some common types of splitting or some common types of signals that you see in an NMR spectrum? Well, we're going to go over 3 that you're going to see a lot. A tert-butyl group, an isobutyl group, and I thought I had an ethyl group in here. Yeah, the ethyl group is here. Okay, so here are the 3 things you're going to see a lot of. Okay, an ethyl group, when you see a triplet that integrates for 3 protons, and you have a quartet at a higher field or more down field that represents 2 protons, you've probably got an ethyl group. What about a tert-butyl group? Right, this is a tert-butyl group right here. A tert-butyl group has 9 protons in it that are all chemically equivalent. But if you go to the next door neighbor, this carbon right here, this would be the vicinal carbon, right? The next door neighbor carbon, it has no hydrogens attached to it. So if we have N+1 and we have 0 + 1, we get 1. And so we get a singlet that integrates for 9 protons. So if you see a singlet that integrates for 9 protons, it's pretty much a dead giveaway that you've got a tert-butyl. What about an isopropyl group, right? An isopropyl group looks like this. Okay, this is just another representation of it here. Well, these 2 methyl groups are both chemically equivalent. There's 6 protons total, but they're split by this one next door neighbor. 1 + 1 is 2. So if you see a doublet that integrates for 6 protons, and you see the 1 proton here, this methine proton, is split by all 6 of these. 6 + 1 is 7. So if you see a septet that integrates for 1 proton and a doublet that integrates for 6 protons, you've probably got an isopropyl group. Now again, complex splitting, I'm going to skip that today because I've done a lot of talking and I want to take a look at some more practice problems. But again, I might come back to this if there's, or time permitting, I should say. A little more information about splitting, just a little more information, then we're going to take a look at some practice. We've got 2 practice problems that I want to look at before the class is over. So 2 more slides and then we'll look at some practice. The first one is if you have an alcohol, if you look at ethanol, which is this molecule here, if we draw out the whole Lewis structure, you have CH3, okay, you have CH2, right, and then you've got a carbon. Sorry, Mr. Dion is tired. There you go. So there's my ethanol molecule. Well, this group right here, right, this is an ethyl. And so that is why we see the quartet that integrates for 2 protons and the triplet that integrates for 3 protons. I've already gone over that. It might be a knee-jerk reaction, and it wouldn't be a bad one for you to assume, well, this proton that I have circled in yellow, the alcohol proton, it should be split by these 2 protons because you go 1, 2, 3, right? They're next door neighbors, okay? In fact, they're not, the alcohol proton is not split by anything, okay? It actually shows up as a singlet. And that is normal. And the reason why is because the hydroxyl proton is labile and on exchange with other protons in the solvent or other alcohol protons when there's just even a trace amount of acid. And so it's kind of like the shutter speed of a camera being slower than the object that's moving. And so it can't capture the proton just sitting there and being split. It's kind of blurred. And so that is why we always end up with a singlet. Another example that I didn't put in my slides, but is mentioned in the textbook, is that this proton of an aldehyde, let's say you have, 2 protons here, you might think, well, the aldehyde proton is going to be split by these 2 next door neighbors. In fact, it's not. So aldehydes usually do not split together or split either. So we'll say not split. Okay, there we go. Okay, well, with all that in mind, now let's turn our attention in the last few minutes to try to solve some problems where we actually look at multiplicity. Okay, so we'll start with this compound over here. We've got a ketone in the molecule, and we've got an ether in the molecule. Let's start with the 3 protons over here. So we have a methyl group, CH3. All 3 of those protons are equivalent. Could anybody tell me, would these give you a singlet, a doublet, a triplet? Does anybody have a feeling about that? Anybody have a feeling? Well, remember that in order to apply the splitting, right, I go to the next door neighbor, right? I'd have to go to the next door neighbor. So the next door neighbor is this carbon right here, which has no protons attached to it. So I would apply n plus 1, and it would be 0 plus 1, and so I end up with 1, and so this would give me a singlet. I'd end up with a singlet for that methyl group. What about this methylene right here? Does anybody have a feeling about the splitting for this methylene? Will it be split by any of their protons? The answer is no. There's no protons on this next door neighbor, and there's definitely no protons on this oxygen, and so it is not split. Therefore, this one will also give you a singlet. Okay, what do we have over here? We have an isopropyl group. Right, we have an isopropyl group. That means that this hydrogen here, right, this guy is coupled next to all 6 of these protons, this CH3 and this CH3, which are chemically equivalent. And so we have n plus 1, which is 6 plus 1, and so we get 7. So for this proton, we get a septet. And for the green protons, these ones here, we have n plus 1. The next door neighbor is this methine. We have 1 plus 1, which equals 2, and so we get a doublet for those 6 protons. Let's try the next one. We have a diketone. We could start by probably, you notice that there's a plane of symmetry down the molecule, isn't there? Right? We have a plane of rotational symmetry down the molecule. And so this methyl group and this methyl group will be chemically equivalent. What will be the multiplicity of these protons that I have circled in yellow? Well, they're going to be split by the 2 protons here, right? Same thing here. These 2 protons We're going to split, and again, they're all chemically equivalent. So for these methyl groups, we're going to have N plus 1. We have 2 neighbors plus 1, so that means we're going to get 3. That means the yellows are going to give you a triplet. The ones in red, there are no protons on the carbonyl, but there are 3 protons in yellow, aren't there? So here we get N plus 1, and we have 3 neighbors plus 1, which gives us 4, and so we're going to get a quartet for all the red protons. Okay, I'll just throw this out here to my students. I have a CH here, don't I? Right, I have a CH, I have a methyne. Can anybody tell me what the multiplicity of that methyne would be? Exactly, it's going to be 4 because it's only split by the 3 protons that I have written in green. So I have N plus 1, and it's going to be 3 plus 1, which gives me 4. That means I have a quartet for this guy. And for the green protons, they're all chemically equivalent. They're only split by this one blue proton that's here. Maybe I'll write it a little neater. The one blue proton here. And so for the methyl group, I have N plus 1. I have 1 next door neighbor, so 1 plus 1 gives me 2. And so for that methyl group, I get a doublet like that. And that is how we determine multiplicity. Let's try another problem. 15.17, it says here are some NMR spectra. Identify whether these compounds are likely to contain an ethyl group, an isopropyl group, or a tert-butyl group. What about an A? Could anybody tell me which one of those groups are an A? And I'll help you out. One of them is an A. No, it's not a tert-butyl because a tert-butyl is going to have a singlet that integrates for 9 protons, right? If we back up here. Again, a tert-butyl has a singlet that integrates for 9. We go back here. We don't have any singlet that integrates for 9 protons. Yeah, there's an isopropyl group, right? These 2 signals represent an isopropyl, right? Remember, in an isopropyl, you have a methyne and 2 methyl groups attached to it. Okay, the 2 methyl groups are split by 1 proton. There's a total of 6, so we get a doublet that integrates for 6 protons. And the methyne proton is split by all 6 of the methyl protons, so 6 plus 1 gives me 7. So I end up with a septet that integrates for 1. If you're wondering what the heck is going on here, since this signal is so small, what this is called an expansion. Okay, this is called an expansion, and it's exactly what you think it is. They're just blowing it up so you can see it more clearly. That there are 1, 2, 3, 4, 5, 6, 7 total peaks in the signal. All right, what about the next one? Anything that anybody recognizes in the next one? I'll give you a clue. In this one, there are 2. Does anybody recognize anything in this one? There are 2 common groups in this one. Yeah, thanks, Alexis. There's an ethyl and an isopropyl, right? We have the doublet that integrates for 6 protons. We have the septet that integrates for 1 proton. Those come from an isopropyl, right? And then we have a triplet that integrates for 3 and a quartet that integrates for 2. And those come from an ethyl group, right? Because in ethyl group, we have CH2, CH3, right? This one is going to produce a triplet, and this one is going to produce the quartet. So we end up with an isopropyl and an ethyl group in this one.